Hello, this is again a session on quadrilateral. Previously we have discussed on angle sum property of a quadrilateral, and I had taken a couple of questions on that theorem as well. Herein we will be discussing very shortly or briefly about various types of quadrilaterals, and then we proceed with the theorems based on these quadrilaterals. The first one we discuss here is a trapezium. What is a trapezium? I draw a figure on trapezium. Trapezium is a quadrilateral with one pair of parallel lines. The basic property is one pair of parallel lines. In this figure, I have drawn not that accurately A, B and D, C to be parallel. Then comes isosceles trapezium. Oh, I misspelled it. Isosceles trapezium. Not much difference, only when in the same figure and the same property wherein AB is parallel to DC, but the non-parallel sides. In this figure, if I take the same figure, the non-parallel sides are AD and BC. They are equal. This trapezium becomes isosceles trapezium. The non-parallel sides are equal. Okay, this is about trapezium. Then comes a parallelogram. I again name it as A, B, C and D. This is a parallelogram. Just have to recall what about a parallelogram. Parallelogram is a quadrilateral with both pairs of opposite sides are parallel as well as equal. That means in this figure, AB is parallel to DC and BC is also parallel to AD. This is the basic requirement. If both the pairs of the sides are parallel, you don't need to prove them to be equal. Okay. Then comes a rhombus. The basic property is all the four sides are equal. I hope it looks like one. Then comes a rectangle, which we have been studying for quite a few years now. Rectangle is this. A rectangle is basically first a parallelogram where opposite sides are parallel and one of each whose these angle to be 90 degree. If this is 90 degree and we first prove ABCD to be a parallelogram, that is AB is parallel to CD, BC is also parallel to CD and only one angle in itself is 90, that makes ABCD a rectangle. Then we have square. Square also we know all four sides equal, as in the rhombus one angle has to be 90 degree, not one angle, actually all the angles them to be 90 degree later on, but if you prove first all sides equal and one angle 90, that makes it a square. Then comes a kite. What is a kite? I draw a figure and then we'll. This is a quadrilateral. I name it as A, B, ABCD. Here it says it has two pair of equal adjacent side. That means these are adjacent side. AB and AD will be equal. Similarly, BC will be equal to CD. Okay, this is a kite. So on a whole, what happens is a square, a rectangle, a rhombus, these are all parallelograms. A kite is though not a parallelogram because opposite sides are not parallel and equal. So we'll keep this as, so these four rhombus, square, rectangle, they are parallelogram. We now move on to taking theorems based on these types of quadrilateral. The first one we say is a diagonal of a parallelogram divides it into two congruent triangles. Oh, I made a spell mistake again. Please ignore this. Let me draw a parallelogram here. It doesn't look one, does it? This is A, B, C and D. A, B, C, D obviously is given to be a parallelogram. You write here, given that A, B, C, D is a parallelogram. To do so, I am using this term to write two parallel lines with a gram. That makes A, B, C, D as a parallelogram. Oh, I need to draw a diagonal of this, and I draw it as AC. We have to prove triangle ABC is congruent to triangle ABC, so it becomes ADC. How do we prove it? We start writing here the proof. Now, as because ABCD is a parallelogram, AD is parallel to BC. In ABCD, AD is parallel to BC and AB is also parallel to CD or DC, yeah. As because, and then if AC is the transversal, then angle DAC and angle BCA will be equal, as because they are alternate internal alternate angles. So I write in triangle ABC and triangle ADC, angle ACB will be equal to angle DAB. They are alternate interior angles. AC is common, and also angle as because AB is also parallel to CD, this angle becomes alternate interior to this angle, So we write angle BAC to be equal to angle AC DAC angle DAC for the same reason, alternate interior. So by ASA congruency, we prove the congruency of triangle ABC with triangle CDA. So a diagonal of a parallelogram divides the parallelogram into two congruent triangles. This was the first theorem. Let us move on to the second one. Says in a parallelogram, opposite sides are equal. I again draw a parallelogram here. We name it as A, B, C and D. We have to prove, this is given to be a parallelogram, we have to prove AB equal to CD and AD equal to CB. Let us draw a diagonal. In the previous theorem, we have proved how these two triangles are congruent. I am not repeating the congruency equalities. By ASA, we had proved the congruency of triangle ADC with triangle CBA by ASA. So by CPCT, we can say BC is equal to DA and CD is equal to AB. This is corresponding part of congruent triangles that proves opposite sides of a triangle to be equal. The next theorem, we write it here. I divided the board. The opposite angles of a parallelogram are equal. We take the same figure as I drew before this one. The same method follows. We prove the congruency of triangle ADC with triangle CBA by ASA congruency, thereby making angle B equal to angle D by CPCT. So this is equal to this, we can say. Otherwise, if you draw the diagonal BD and prove the congruency similarly for triangle BCD and triangle DAB, thereby making the opposite angles, angle A and angle C, to be equal. Thereby the opposite angles of a parallelogram are equal. We move on with the next theorem. The next theorem says the diagonals of a parallelogram bisect each other. So I draw a figure again. Even I will draw the diagonals. We will prove A, B, C, D. It's given A, B, C, D is a parallelogram. B, D, A, C are the diagonals. We have to show that they bisect each other. If this is the point of intersection, we have to show that OA is equal to OC and OD is equal to OD. So here it is given to us A, B, C, D is a parallelogram. To prove AO equals CO and BO equals DO. Now let us take triangle AOB. Oh, sorry, I'll clearly write it. AOB and triangle COD. These two triangles, what I mean is this triangle and this yellow triangle. COD, sorry, I'll use the brighter color. COD do we need COD or we don't need? Because what I can see, okay, we don't need actually. So AB is equal to CD, right? They're opposite sides of a parallelogram. We have proved them to be equal. Now this angle, angle 1 will be equal, angle 1, 2, 3 and 4. Angle 1 will be equal to angle 3, alternate interior. Angle 2 will be equal to angle 4. So again by ASA criteria, we prove them to be, these two triangles to be congruent. Now by CPCT we can say DO is equal to BO. This is derived from congruency of AOB and COD. Similarly, you can take the congruency of these two triangles. Sorry, I made a mistake there. Okay. Now we prove the congruency of these two pink triangles, and by again the same application of ASA. I hope you can do that by yourself. Name them as 5, 6 triangles, 5, 6, 7, 8, and you will be getting AO equal to CO again by the CPCT of proving the congruency of these two pink triangles. Hope you can do that by yourself, this part. Thank you.